Hello and welcome. Dual active bridge converters are widely used for many power electronics applications, including electric vehicles, uninterruptible power supplies, and power converters for energy storage management systems due to their appealing topologies and qualities. In order to help meet the increasing demand for control testing for these applications, the 2022.4 Typhoon Hill Control Center software release includes a new dedicated DEF-PGA block that provides fast calculations for dual-active bridge converters with a 50 nanosecond simulation time step. It is specially designed to fulfill the needs of high-frequency DC-DC charger applications. Since the minimum simulation time step for currently available Hill devices is 200 nanoseconds, this specialized DC-DC converter solver operates independently from the rest of the circuit and provides simulation results at the specified simulation time step of the model settings box. This component acts as a current source inside the circuit. State calculation of the dual-active bridge component is performed every 15 nanoseconds. However, calculation results must be uploaded at the rate of the simulation time step for the rest of the circuit. Considering that, the dual-active bridge solver will take all values calculated during the simulation time step and, after the simulation time step expires, calculate the average value and provide this to the component's outputs. For this reason, you cannot observe the values of the variables inside the dual-active bridge converter with a 50 nanosecond sample frequency in SCADA, nor at the analog outputs of the Hill device. Those values are kept inside the FPGA block, and only the average values are accessible and displayed. The dedicated dual-active bridge solver utilizes the switch-level GDS oversampling method with a 3.5 nanoseconds digital input sampling period. This solver is available only for Hill 404 and Hill 606 devices with a specially provided firmware configuration. Calculating the dual-active bridge state every 50 nanoseconds along with switch-level GDS oversampling provides high fidelity and accurate results, which is especially important for converters with higher dead time values. Let's see where to find this new component and how to parameterize it. Inside the converters library category, a new enhanced resolution subfolder is added. Clicking on this subfolder reveals the new dual-active bridge component. Let's drag and drop it into the model. In the component dialog box, you can find control, electrical, and extras properties. Gate drive signals for switches within dual-active bridge converter can be provided on HIL device digital inputs or generated by FPGA's internal PWM modulator. In Electrical Properties tab, you can define values for series inductance, series resistance, and transformer turns ratio. Transformer within this component is modeled as ideal, meaning that winding inductance and resistance are dispensed. There is optional possibility to include series capacitor in the circuit as well. In Extras tab, you can define short circuit resistance values for both H-bridge inverters and limit the signal access. Now, let's see how the component works in practice. This circuit consists of two voltage sources that exchange power via a dual-active bridge bidirectional converter. Input and output LC filters remove higher harmonics and smooth out current and voltage signals. The dual-active bridge converter is controlled via gate drive signals generated by an internal modulator inside the component. The switching frequency is 250 kHz and the dead time is 200 nanoseconds. The control principle, which is implemented directly in this model, is based on changing the phase difference between the carrier signals for two inverters while keeping the same duty cycle. By changing the phase shift, we obtain a wide range of output voltages as well as control over the power flow direction. Since the phase shift determines the power flow direction and output voltage, we'll use a SCADA input component to set the phase shift in runtime and simulate a diverse set of test cases. Now, let's compile the model and load it to the Hill 404. The phase shift value at the simulation onset is 30 degrees. By applying this value, the power flows from voltage source number 1 to voltage source number 2. However, by setting the phase shift to minus 30 degrees, we change the power flow direction, causing power to flow from the right side to the left side. To have clear insight into the dual active bridge solver capabilities and advantages, let's look at how the same electrical circuit performs outside of the constraints of real-time testing. The results displayed here show the output current as a function of the phase shift angle. The red curve represents the current values calculated in the non-real-time VHIL+ environment with a 10 nanosecond simulation time step. The green curve represents the current values calculated in the real-time environment, utilizing the new dual active bridge 15 nanosecond time step solver with a 200 nanosecond simulation time step for the rest of the circuit. We can see that by using the dual active bridge converter solver, we get very similar results in real-time simulation as those that we can achieve when simulating in non-real time with a smaller time step. We hope that this new dual active bridge component will help you develop for high-frequency control applications, and we look forward to your impressions. Thank you for watching.